Ji, Assalamu alaikum. Uh, in the last short videos, I discussed with you the accelerated version of the switching power supplies like flyback converter, forward converter, and the push-pull converter. In flyback converter, we saw that operates entirely differently from that of the forward converter and the push-pull converter. I mean, in the flyback converter, the when primary winding is conducting of the transformer, the secondary winding is off, and when the primary winding is off, then secondary winding conducts, and the energy is stored in the form of in the gap of the ferrite core is transferred to the output when secondary windings conduct. In forward and push-pull converter, we saw that when primary winding conducts, then at the same instant secondary winding conducts, and the energy is transferred instantly. But we also saw that there was flux imbalance problem both in forward converter and the push-pull converter, and for the forward converter to rectify the flux imbalance problem that can saturate the transformer, we utilize a reset winding across the primary winding, and for the push-pull converter we saw that in the push-pull converter, the primary winding was acting just like the seesaw action, and the flux imbalance problem exists due to the slightly different on times of the both conducting MOSFETs, and which can this flux can staircase in one direction and can saturate the core. We saw that in the forward converter, the maximum voltage stress on the MOSFETs was twice that of the rectified DC input voltage, and in the push-pull converter we saw that the maximum voltage stress on the primary MOSFETs was also twice the rectified DC input voltage, plus 30% leakage voltage spike on the primary winding. So that is why these two topologies can be used where the mains AC voltage is less, like in the countries where it is 110 volt AC, or where the DC voltage is also less. In today's short video, I will discuss with you another switching power supply topology, which is also the isolated power supply version, and it is called the half bridge converter. In half bridge converter, there is a phase lag consisting of the two transistors connected in series, whose one point is connected to the rectified DC input voltage and other point to the input ground. And similarly, another phase lag consisting of the two capacitors connected in series, whose one point also connected to the rectified DC input voltage and other point connected to the input ground. And the primary winding one point is connected to the middle of the both transistors, and the other point of the primary winding is connected to the middle of the both capacitors. In the half bridge converter, there can also be the issue of the flux imbalance problem, but it is not that severe as we saw in the forward converter and the push-pull converter, because the flux imbalance problem can occur in the half bridge converter because of the reason that the two capacitors can have the different charges on them, hence slightly different voltages on them, that can create the different volt seconds on the primary winding. And so flux can staircase in one direction and can saturate the core. To avoid the flux imbalance problem, though it is less than forward converter and the push pull converter, we insert a small capacitor in between the primary winding one point, and the other point of this small capacitor is connected to the middle of the both capacitors. The purpose of the blocking capacitor is to isolate the DC voltage of the middle point of the capacitors from the primary winding, and only AC voltage can pass through the primary winding. So there is no issue anymore of the different volt seconds on the primary winding. Another rectification can be done in the form of the bleeder capacitor connected across the both capacitors, so that they store the equal amount of charge on both of them, hence the equal voltage on both of them. As I told you that the maximum voltage test on the MOSFETs in the half-bridge converter is only DC rectified voltage instead of the twice DC voltage as we saw in the forward converter and the push-pull converter. So that is why the half-bridge converter can be used easily in European countries and Asian market, where the mains voltage is 230 volt AC. The maximum power that can be delivered from the half-bridge converter is around 500 watt. Because if we go above the 500 watt, then the primary current would be large in amount, and we need to install high current MOSFETs or BJTs, and which is not a cost effective solution, or maybe not available easily. The secondary side of the half-bridge converter is identical to the push-pull converter, and because the two MOSFETs, series MOSFET in the half-bridge converter conducts 180-degree out of phase, so there are two pulses on the secondary side, and hence the small LC filter is required to convert it into a pure DC output voltage. As compared to half-bridge converter, the forward converter, in forward converter there is only that operates only less than 50%, so there is only one pulse in the output in a switching cycle, and hence the frequency is less, and the LC filter is required for that. So this is an advantage of the half-bridge converter and the push-pull converter. The half-bridge converter, example of the half-bridge converter that you can see in their daily life is in the form of the ATX power supplies, which are used in the tower casing computers, and the power output of these RTX power supplies is normally 350 watt or 400 watt. This was today's short video about the half-bridge converter. And in half-bridge converter we saw that the maximum voltage test on the primary side MOSFETs is only VDC, I mean the rectified DC input voltage, instead of twice the DC input voltage which was in the forward converter and the push-pull converter. And we also saw that in half-bridge converter the energy is transferred instantly to the secondary side when the primary winding conducts. So this was a today's short video. So stay connected, and thank you very much.